So we'll go to the next order. Remember, we take the some space here. But anyway, this is done. We'll do it again, or do the part of that. We'll refer back to the electric dipole, because when you talk about magnetic dipole, there's a symmetry between magnetic dipole and electric dipole. Just like electrostatic and magnetostatic, the dipole field are very similar. But first, we need to get to the dipole field, dipole term first. Now, we just need to go back to the Taylor expansion that we had 9.9 and take just the n equals to 1 term. Go back a little bit over here. Okay, so start from equation 9.9 with n equals to 1. So we just finished n equals to 2, n equals 0, which is the electric dipole. Now for n equals 1, there are actually two parts. And we'll separate the two parts first and then discuss the one after the other. Right now, the separation looks a little arbitrary, but it turns out that the reason for that is the form of the final result is somewhat nice in some sense, that we can corresponding to what we learned from like electrostatic or magnetostatic. So like one is the magnetodipole, the other is electric quadrupole. So we'll make that arbitrary separation. But that what by convention people like to do that. So just follow this. So magnetic potential, we have the usual coefficient mu c over 4 pi, the e to the I k r, the propagating phase, and then R. Now n equals to 1. You have a minus I k to the n power, so it's 1 divided by 1 factorial, which is 1. And then you integrate j as a function of x pi, and n is the unit vector, which is basically just the R unit vector n dot x pi. To the n power, not this n, it's the integer n. The n is 1, so it's just keeping this one. Okay, so that's the n equals to 1 term. But then I'm using a simplified version than Jackson. Jackson actually keep one more term in 9.30, but in radiation zone that the other term is we will ignore anyway. So we'll just start with the simplified version, just keeping the term in the radiation zone. Okay. Now the idea is to separate this one into two terms. Okay. So the rest is just outside the integral. What we are concerning is what this integral is. So, but before we do that, we separate that into two terms. Okay, so this integral, we have j x dot x pi. We actually want to solve first divided by 2. So you have half of that, and then plus another half of that. Okay. And then you add and subtract the same thing to basically add 0, but then after you add that, you basically separate that naturally separate into two parts. So first is adding, actually subtracting. Something is similar. As, the other one we basically is similar to that, but we want x along the x point direction of n dot into j. want to subtract that. So in order to subtract that, we need to add it back so that the total is 0 at x pi. Okay, so you know I'm doing. But separate it into two half, and then minus this plus the same thing. It's okay, and everyone can follow. This is kind of important how you solve that, how you separate it the two. And now actually you group this in the square bracket as one term, and then the other in the other bracket is another term. And the first term turns out to be the electroquadruple term, and the second one would be the magnetic dipole term. Okay, so that's how you separate the two terms. But before we do the integration, we will usually put in a form that we can easier to recognize what they are. And for this one, if you remember the triple product of the triple cross product, and this is of the form, a triple cross product will change to this form. If you remember that, this is just this part. This 1/2 factor is basically n crossed into or you can say that because this is the first term is j, but we want x cos j inside, so we can say it's x cos j is x cos into n, right? So that this triple product, the first term is j is x dot n, and the second term is along x and n dot j, right? So that is more like a magnetic dipole. If you remember the magnetic dipole, we divide chapter 5, and now you combine, and we'll consider this later. The first term is electroquadruple. We'll do that a little later. So combine this with the factor just for the second term. Okay. We actually want to do n cos into this one, so you change the direction. We have a negative sign, but cancel with this negative sign. I use of c for 4 pi r cos into this one after you do the integration. So basically, this is the integration 1 of x pi cos j as a function. Right, and that one, I think, if you look back to chapter 5, this is what we define as the magnetic dipole. Let me look up the equation number. We must talk about that in chapter 5. Right. It should be 5.54. Yeah, that's exactly right. 1/2 of x pi cos in the j, and do a spatial integration. Okay, so this is exactly the same. Although that one is a magnetostatic, this is just the spatial part of the oscillating field. So you have the usual e to the minus I omega t factor. But just the spatial part is this magnetic dipole. So you can simplify that as I u sub c, okay, kr, not kr, n cos m. Okay, now that is the magnetic potential, and after this, then the rest is just to take a integration, differentiation to get the H field and E field, because curl A is B and B over mu 0 is H. And then you can either use the Faraday's law or the Ampere's law to get E from H. But then there's a trick, kind of, Jackson used that, because you remember that this is magnetic dipole, right? But the electric dipole, we have something similar. Although Jackson keeping the near field term also, and this trick is even more useful for the near field term, but we are ignoring the near field, we just keep the radiation field. So, but we use this by just like analogy. Just basically the mathematical form is similar. So basically, you go back to equation 9.8. This is for electric dipole. The H field is C. I'm keeping just the radiation. So k to the square for 4 pi r to the minus either I k r and n cos p. So this A is like a very similar to H. We have everything similar to n cos something similar to n cos p. And now the next one for the magnetic dipole, you need to do a H field. H field is basically 1 over mu 0 and then curl of A. So basically taking a curl and then divided by the mu 0, you get H. And then but for the electric dipole, we are doing something similar. We're actually using E is using 9.5. We can use the 9.5. E is I z 0 over k curl of H. Right. Then in that case, that one is the same. So this is very similar to this. Your n cos p, this is n cos m, and then you take the curl, and then you take the curl of that, right? For the dipole, for the electric dipole, this calculation is straightforward. This becomes the end result is this is just the first term in the second equation, 9.8 over 4 pi equal 0 k squared n cos b cos a into ITL. Okay, so I mean, we don't have to do this because we actually doing a derivative in the fossil is easy. We talked about that a few times, and we don't have to do that. But if you just by analogy, then the H field in the for the magnetic dipole term is also straightforward. That would be similar to this one. So you just need to work out this this coefficient, if the difference in the coefficient. This is, you have this I mu 0, this is C k square. And this is M, this is P, and all that. And then there's mu 0, there's all these other parameters. But if you keep track of all these parameters, then you can calculate H field for this case, which is straightforward, k squared over 4 pi. Instead of n cos p cos n becomes n cos m cos n. Obviously, you still have all these just like that. Okay, and so I mean, Jackson again. The Jackson used this kind of analogy because you take in the Lie field. The Lie field, if you do that, then you save a lot of work. But for us, it doesn't matter. But anyway, once you have the H, you can calculate E again. So E, you can use this. You can use this on this H again to calculate E. Or you, this is coming from the Ampere's law. You get that. But if you use the Faraday's law, it's also okay. Faraday's law, you have a partial B, partial T, which is minus I omega B. It's curl E, minus curl E, minus curl E. Right. So, and then you compare with this one, right? So you can say H is mu 0 over H is B over mu 0, which is in this case you cancel this, but divided by I, multiplied by minus I, divided by mu 0 over here. Curl E. Okay. Now you can compare with this one, the mu 0, and you can just use the, because you have a curl A here, this is curl E. I mean, normally you cannot identify if this equals to that. That doesn't mean that the operator, I mean, curl operate on something. This is curl operate on something. It doesn't mean that whatever you call operate on, they are equal. That is usually not the case, but in this case, they are. I mean, there are reasons for that because they are equal up to a gradient function. But in this case, because the divergence A is 0, you can check the divergence A is 0 in this case. And then also divergence E should be 0 because there's no charge in the radiation zone. So therefore you can compare this with that and say that the E is just, you can say the rest is A, B is curl A, where you can get rid of that. And so minus I, E is A, so A is, what is minus I, so I, A times omega. Right? And in that case, you can substitute A into here. Cancel with I times I is minus 1. That equals to mu 0 omega k 4 pi to 0. 4 pi r, so 4 pi r. So I is minus, there's a minus sign. And then phase vector and cos m. Okay, so that should be the first term in 9.39. So again, the G Jackson uses Z sub 0, which should turns out to be exactly the same. Right? Because omega is C times K, so that becomes C K squared, and C is 1 over mu 0 epsilon 0, and multiplied by mu 0, you get this C sub 0 is the same. Okay, and now we have everything. We have E and H, E in here, H in where? H in here, right? And then because of that, we can calculate um, we can calculate the dp omega. And so remember that space. The dp omega it's in the radiation zoom, we basically use the single frequency formula, 1/2 the mu part of E dot E and E cos H and multiplied by R squared, because we're talking about R solid angle, and dot into the n direction. Okay, so we did that for the electric dipole, but now the magnetic dipole is very similar, because for electric dipole, H is this one. So you see that H is very similar to this E. H is similar to E. And E in the electric dipole is this one. And E is very similar in form of H. As it turns out that you can identify a transformation. Jackson pointed that out in the if you start with the electric dipole terms and then do this transformation, then change E to C0H and C0H to minus E and P to M over C. Then you change this two formula to this two formula. Okay, you can do that kind of check. You can check a little bit like that. So if E turns to C0H, so this becomes C0H, so it becomes C0 times H. So you have a C0 in here, and or to change that, so this becomes C0. So you have C0. So H will be this one divided by C0. But then P change to M over C, so M over C, and the rest is like the start of with this using this formula. So this imply H is equals to K squared over 4 pi epsilon 0 C sub 0, because you divided by the C sub 0, and cos M over C cos M, and then the phase factor. Right. Copy everything. Okay. And you can see that this should be equals to that one. So again, you have a C, and C is 1 over mu 0 square root mu 0 epsilon 0. Oh, you can work out all these factors. So epsilon 0 C0 C is epsilon 0 square root mu 0 plus 0 square root epsilon 0 mu 0. They actually cancel, everything becomes 1, right? This, this and that is epsilon 0. This cancel, this is 1. Okay, so all this becomes 1. The rest is k squared over 4 pi. And the rest is just this one, right? And then you can also do that for this one. So E H field in this and turn it to minus E. So basically, this is minus E divided by H C of 0. So E will be this multiplied by C of 0 after you change P to the M over C. And you see that it actually works out, including the minus sign. It will work out. And the idea is that once you realize that you can do that transformation, you can use the electric dipole dp d omega to change that to a magnetic dipole term without doing the things. So basically for electric dipole, this is 9.22. So C squared C sub 0 32 pi squared to the 4th and cos E cos N squared. Okay, and then for this one, this basically changes that to exactly the same. Because, I mean, just look at this one, E changed to Z0H, and H changed to minus E divided by C0. So C sub 0 cancel, become H cos E complex conjugate, but you take the real part, so you can put the complex conjugate in either quantity. And then, so they are exactly the same, right? They're exactly the same. And so all you need to do now is just change P to M over C, and you get the formula from the dipole, which Jackson didn't write it down, didn't bother to write it down. So basically, only this one is important now. Just change P to M over C. Yeah, C squared also. Okay, that would be your power for the magnetic dipole term. Okay, and I mean this is the general formula. Again, you can also use the special case when M is real or in phase, or component in phase, and get similar to 9.23, except P changes to M over C. And likewise, the total power, 9.24 also do the same substitution. You get the total power from the dipole term. It's okay, this, I mean, we don't have to do it. We can do it again and just use the magnetic dipole term and then do this cross product again. And you see, you still get exactly the same. But what Jackson noticed is there's some similarity between the electric dipole term and magnetic dipole term. You can change one set of equation to the other by this transformation. It's just basically a mathematical analogy. Okay. So that is what it is, and that will save you time. And Jackson did that. It's okay. So that's the magnetic dipole term.